Welcome back to AI Teaching Gen AI System Design. Today, we tackle Gmail Smart Compose, suggesting the next words as users type emails. We'll follow a structured approach, clarify requirements. Should suggestions be personalized? What languages and data are available? Do we need real-time predictions? Frame as ML task. Input is typed text. Output is the next few words, a text generation problem. Transformers are ideal for handling long-range dependencies efficiently. Data prep, clean, normalize, and tokenize large volumes of email and general text. Model development, use a decoder-only transformer with embeddings, positional encoding, attention, and a prediction head. Training and fine-tuning. Pre-train on general text, then fine-tune on emails. Generate suggestions with beam or greedy search. Evaluation, offline metrics, perplexity, ExactMatch N, and online metrics, engagement, latency, quality. System design, triggering service, phrase generator, and post-processing ensure relevant, safe, and fast suggestions. By combining these steps, we build a smart compose system that's accurate, responsive, and user-friendly. The problem is to design Gmail Smart Compose, which assists users by suggesting the next few words as they write an email. Shall we consider personalized suggestions? How much training data do we have? What languages should we support? How many active users of Gmail should we make real-time suggestions? To design Smart Compose effectively, we need to clearly frame the problem as a machine learning task. Model input. The input to our model is the sequence of words a user is currently typing, essentially a partial sentence or phrase. Second model output. The model's goal is to predict a natural, coherent continuation of that sequence, suggesting the next few words the user might want to type. Third task, type. This frames the problem as a classic text generation task where the model generates plausible and contextually relevant text based on preceding context. Fourth, model choices. Historically, recurrent neural networks, RNNs, were used for sequence data because they process words in order, maintaining a memory of prior inputs. However, they struggle with long-range dependencies and slow training due to their sequential nature. More recently, transformers have become the architecture of choice. They leverage parallelism during training and better capture long-term dependencies via the self-attention mechanism, making them more efficient and effective for text generation tasks like Smart Compose. By framing the problem this way, we lay the groundwork for choosing the right modeling approach and training methodology to deliver fast, accurate, and context-aware suggestions to users. Data preparation is a crucial step for building an effective Smart Compose model, ensuring that the raw input is transformed into a format the model can understand and learn from. 1. General data and email. Data, we start with a large corpus of email data, which includes user-generated text, email threads, and typical conversation patterns. This data is highly domain-specific and reflects real user language, making it valuable for teaching the model how people naturally compose emails. 2. Text cleaning and normalization. Raw email data can be noisy. It may contain typos, inconsistent casing, special characters, signatures, or quoted text from previous messages. Cleaning involves removing irrelevant parts, normalizing case, fixing common typos, and standardizing formats to create a consistent input for the model. This step helps improve the quality of training data, reducing noise that could confuse the model. Third, text tokenization and token indexing. Once cleaned, the text is broken down into smaller units called tokens, which can be words, subwords, or characters depending on the tokenization strategy. Each token is then converted into a unique numeric ID, producing a sequence of numbers that the model uses as input. This numeric representation is essential because models like transformers operate on numerical data rather than raw text. In summary, careful data preparation transforms messy email text into clean, standardized, and numerical sequences that enable the Smart Compose model to learn meaningful patterns for predicting user input effectively. When building Gmail Smart Compose, our goal is to suggest the most probable next words or phrases based on what the user has already typed. To do this effectively, we need to choose the right transformer architecture. There are three main types of transformer models: encoder-only transformers. These read the entire input sequence and produce a contextual representation for each token, which is then used for classification or labeling tasks. For example, BERT is commonly used for sentiment analysis, where the model predicts whether text is positive or negative, or named entity recognition, where it tags entities like names, dates, and organizations. However, encoder-only models don't naturally generate new text, so they aren't ideal for Smart Compose. Decoder-only transformers. These process the input and then generate new tokens one at a time, each step conditioned on the previously generated tokens. Models like GPT-4, LLAMA, and Gemini follow this structure, which is perfect for text generation tasks. Exactly what Smart Compose needs. Encoder-decoder transformers. These combine both components. The encoder builds a representation of the input, and the decoder uses it to generate an output sequence. This is the classic setup for machine translation tasks, where the output is a transformed version of the input. For our use case, decoder-only transformers are the best choice, because we only need to generate continuations of what the user has typed, not transform the entire message. Here's how the model processes text in Smart Compose. Text embedding. Every word or subword token is mapped to a fixed length vector representation. These embeddings capture semantic information so that words with similar meanings are close in the embedding space. Positional encoding. Since transformers don't have a built-in sense of order, we add positional encodings to embeddings to indicate the position of each token in the sequence. These can be fixed sinusoidal patterns or learned embeddings. Transformer block. Multi-head attention. This mechanism lets each token attend to other tokens in the sequence, focusing on relevant context. In a decoder-only setup, each token can only attend to preceding tokens to prevent cheating by looking ahead. Multiple attention heads allow the model to learn different types of relationships in parallel. Feed-forward network. Each token's embedding is passed through two fully connected layers with a ReLU activation in between. This transforms the embedding further, enabling more complex feature extraction. Prediction head. The final layer maps the updated embeddings into a vector of probabilities across the vocabulary. The highest probability token is selected as the next suggestion, and this process repeats until a stopping criterion is met, e.g., end of sequence token or user input interruption. By structuring Smart Compose around a decoder-only transformer, we can continuously predict the most relevant continuation of a user's email with minimal latency, making suggestions that feel both accurate and natural. In the training phase for Gmail Smart Compose, we follow a two-stage training process, pre-training followed by fine-tuning, to balance adaptability, efficiency, and performance. The pre-training stage is where we train a decoder-only transformer on a very large and diverse corpus of general text data sourced from the open web. The goal here is not to immediately solve email composition, but to teach the model broad language patterns, grammar, semantics, and world knowledge. The training objective is next token prediction, meaning the model learns to predict the next word or token given the previous ones. We use cross-entropy loss to quantify how well the model's predicted probabilities match the correct tokens. An important efficiency advantage is that the transformer processes all token positions in parallel, which speeds up training compared to sequential models like RNNs. Once the model is pre-trained, we move to fine-tuning. This is where we specialize the model for Gmail Smart Compose. Here, we adapt the pre-trained weights to a massive domain-specific dataset, in this case, 1 billion anonymized emails. The objective and loss function remain the same as in pre-training, but the data distribution now closely matches our target use case. This approach improves generalization while also allowing fast convergence during fine-tuning, since the model starts from a strong language foundation. Fine-tuning also helps mitigate overfitting, especially when domain-specific data is smaller than the open web corpus. After training, we need to sample from the model to generate text suggestions. Sampling can be deterministic, producing the same output every time for the same input, or stochastic, which adds variability and creativity. For deterministic generation, two common algorithms are greedy search, always picks the most probable next token, ensuring consistency, but sometimes producing overly safe or repetitive text. Beam search maintains multiple candidate sequences in parallel, exploring different possibilities and selecting the top k most probable completions, balancing quality and diversity. This combination of large-scale pre-training, targeted fine-tuning, and careful sampling is what enables Gmail Smart Compose to produce accurate, contextually relevant, and user-friendly suggestions in real time. Evaluating the performance of Gmail Smart Compose involves both offline and online metrics to ensure the model produces accurate, useful, and timely suggestions. Offline metrics are calculated on benchmark datasets and help us assess the model's predictive quality without involving users directly. Perplexity is a common metric for language models. It measures how well the model predicts the exact next tokens in sequences from the dataset. A lower perplexity indicates the model is better at predicting the true text, meaning it has learned language patterns effectively. ExactMatch N evaluates how often the generated phrase matches exactly the first n words of the ground truth text. This metric shows how closely the model's completions align with expected human written continuations, giving insight into precision at varying phrase lengths. Moving to online metrics, these measure real-world user impact once the model is deployed. User engagement tracks how often users accept or interact with Smart Compose suggestions, reflecting usefulness and satisfaction. Effectiveness measures whether the suggestions actually help users compose emails faster or with fewer errors. Latency is critical for user experience. Suggestions must appear instantly as users type to feel seamless and non-disruptive. Quality captures user feedback on fluency, relevance, and tone, sometimes gathered through surveys or implicit behavioral signals. Balancing offline and online metrics allows us to iterate on the model efficiently while ensuring real-world value. Offline evaluation guides rapid experimentation, while online metrics confirm that improvements translate to a better user experience. Designing Gmail Smart Compose requires an integrated system that delivers fast, relevant, and safe text suggestions in real time. Let's walk through the key components. 1. Triggering service. This module continuously monitors user activity, mainly keystrokes, to know when to activate Smart Compose. It's responsible for detecting when the user starts typing and when the model should generate suggestions, ensuring responsiveness without unnecessary computation. Second phrase generator. At the heart is the phrase generator, which communicates with the underlying transformer model. It uses beam search to explore multiple candidate completions simultaneously, ranking them by their likelihood. To maintain user experience quality, it removes overly long suggestions and filters out completions with low confidence scores, delivering concise, relevant, and reliable text predictions. Third, post-processing service. After the model produces suggestions, this service applies important safety and fairness checks. It replaces pronouns and gendered words to promote gender neutrality, performs lexical analysis to detect sensitive or inappropriate terms, and filters out NSFW content. These steps help prevent biased or offensive suggestions and ensure the feature aligns with ethical guidelines and user expectations. Together, these components create a smooth pipeline, from user input detection to generating and delivering safe, helpful text completions, making Gmail Smart Compose both effective and trustworthy.